Okay, so
Okay.
welcome. We are going to start the presentation of the final work of the master thesis of Joan Cucurul, and the committee will be Gianluca, myself, and Damian. And you have maximum half an hour, I understand, between 20 minutes and half an hour for the presentation, and then we will have the questions.
Okay. Okay, so welcome everybody to my presentation. First of all, I want to apologize for my delay. And okay, let's start. My work was motivated by previous work made by Damian Gumila, reference 1 in this presentation, who proposes a new hidden variable theory for quantum mechanics. Then the goal of my work is to extend this theory in a relativistic context. So first of all, I will explain a little bit the structure of this new theory. And then we will formulate it, but using my starting point, which is a relativistic equation. Then we will discuss some results at the non-relativistic limit, and then at the relativistic regime. Okay. This new hidden variable theory was inspired by a work done in reference 2, where they propose, well, it was done in 2002, and they prove that the Schrödinger equation can be obtained from an exact and constant uncertainty principle. So classical particles following an uncertainty principle in having uncertainty on their momentum and position will follow the Schrödinger equation. But this work did not propose any mechanism for a particle to have these fluctuations. And then the novelty of the work made by Damian Gumila is propose this mechanism. Then the ingredients of this theory are the Galilean version, so at the non-relativistic limit, of the complex sign-Gordon equation, which is the fundamental equation in this theory. And then the two ingredients are the particles, solitons, and a chaotic fluctuating background that gives to these particles the fluctuations and therefore the uncertainty. This new theory is classical, local, and deterministic. And if this has to be a new theory for quantum mechanics, it will have to pass some tests. For instance, simulating a potential, we will have to get the eigenstates of this potential given by the Schrödinger equation. In this theory, we will have to see also quantum interference. And also, this theory will have to pass the Bell test. The idea of hidden variable theories were compromised by the Bell theorem. This theorem states that any theory that fulfills statistical independence before and after the measurements and local realism can't violate the Bell inequalities. And we know for the experiments that the quantum systems violate these inequalities. And also, quantum theory predicts these violations. But the Bell theorem does not constrain our theory because it's deterministic. And then our theory does not have statistical independence before and after the measurements. Then it will be possible in the future that this theory will violate Bell inequalities. Okay. Now we will start formulating this theory from my starting point, which is the complex sign-Gordon equation. It's a Lorentz invariant equation. Then we start from the Lagrangian, we get the equations of motion, and we see that they have a second-order time derivative. Then, if we want to simulate this system, we have to split the equation into defining a new variable, well, a new field, which is the time derivative of the field of this equation, phi. Okay, and then from the Lagrangian, we can obtain the momentum density, the energy density, neither conserve charge, for instance, and everything. Okay. Well, the first ingredient of this theory is this chaotic background. Then, to prove that the complex sign-Gordon equation has this chaotic behavior, we prove that plane waves are solutions of the complex sign-Gordon equation, and that they are unstable. And this is a condition typically leading to chaos. So this is our way of proving that there is chaos in the complex sign-Gordon equation. Then we take the plane wave, a generic plane wave solution, and we perturb the amplitude and the phase with small parameters, well, small functions. And then we perform a linear stability analysis. We put this in the complex sign-Gordon equation, and we get the time evolution expression for the perturbations. And we see that it depends on a parameter, lambda, and we get the eigenvalues of this parameter. And we have 4 of them, 1 negative, 2 imaginary, which usually lead to oscillations, and 1 positive. And this positive eigenvalue leads to instabilities. Here we have this value represented. And then we did also a simulation of a perturbed plane wave. And we see that some modes of this plane wave are excited in the same way that it was predicted by the theory. So therefore, we conclude that there is chaos in the complex sign-Gordon equation. And further characterization of this chaos is left for future work. Okay, the other ingredient of this theory are the solitons, our particles. Here we have the expression of a soliton, where W is the amplitude of the soliton. And in this theory, we will consider small particles. So W being much smaller than 1. Since we are in a relativistic theory, we can boost these solitons. So here we have the general expression of a boosted soliton. And here we have a represented soliton. The blue line is the amplitude. And from here we see that this is a localized structure. So it's a localized particle. And that the real part and the imaginary have oscillations, which recalls a little bit this duality between wave and particle. Okay, then we can calculate the relativistic momentum of the soliton, the mass, and these properties. Okay, now we have to place this soliton in the fluctuating background. There is no problem if we perturbate the soliton with a fluctuating background, because in contrast with the plane waves, solitons are stable solutions of this equation. And they are robust in time evolution. So here we have our final field, which is the soliton, which has the soliton contribution and the fluctuating background. And now, if we want to simulate this or to perform analytical calculations, we have to give initial conditions. Especially, well, we know the initial conditions of the soliton, but we don't know the initial conditions for the fluctuating background. And here we do an assumption, which is that a white noise is a realistic condition of this fluctuating background. No? So that this white noise can be realization of this background at some time. And then we set this as the initial condition. And with this, we give the amplitude of the background, which is epsilon. And we set this amplitude to be much smaller than the amplitude of the soliton, W. Okay, this fluctuating background give fluctuations to the position of the soliton. And here we have the expression to calculate them. Then the expected value or the mean value, if we do a solid ensemble of some solitons, the expected value of the position will be the actual position of an unperturbated soliton. And then with this, we can calculate the fluctuations. Then we calculate the variance of these fluctuations. And after doing some calculus, we get this expression, which has a term that diverges because of L. L is the interval where we perform this integral. And this means that we have to find a sufficiently large L to integrate all the soliton to get his position, but sufficiently small not to integrate all the fluctuating background, because then is when it diverges. And we see that with our assumptions, having a smaller background than the soliton, we can find this value of L. This is more explained in the report. Then, well, we find the value of L and we perform this integral. And we get this expression for the fluctuations of the position of the soliton. Then this fluctuating background, of course, produces also a momentum fluctuations. Here we have the expression of the momentum for this perturbed soliton. And we calculate we find the expression for the fluctuations of the momentum. We find the variance, and we see that we have a term that we don't know how to integrate, but we can make the assumption that this space derivative of the background is much smaller than the amplitude of the soliton, which is realistic because the background has the amplitude of epsilon. But this can lead to some problems at the simulations, because if we give this initial condition of a white noise, the space derivative of a white noise is not a well-defined quantity. Then it depends on the discretization of our simulation. But still, we see that his assumption, at least in our conditions of the simulation, is correct, because we perform we make this assumption, we perform the integral, we get this expression for the variance for low but relativistic velocities, because the calculus for all the velocities is more complicated. And we see that this theoretical value fits with the simulated value at low velocities. Low but relativistic. We are at 0.2, the velocity of light, which is 1 in this case. Okay. Then we see that at the non-relativistic limit, when the velocity is 0, we can get a constant uncertainty principle. This principle does not depend on the properties of the particle, only on the fluctuating background. And then we can use this reference 2 that links the uncertainty principle to the Schrödinger equation. And we substitute our data and we get our Planck constant and our Schrödinger equation. In this case, with 0 potential. And well, we can put a potential in further work. And well, from the Schrödinger equation, we will get rho, which is the modulus of the wave function, which is the probability density function. Okay. And knowing all this, we perform our simulations. The starting point is, the initial condition is a Gaussian distribution. Okay. So the initial condition is a Gaussian distribution. And well, we know the evolution of this according to the Schrödinger equation. So we find the time evolution of the variance of this Gaussian. And we perform a time evolution simulation of, for instance, 4,000 solitons. And we see that both descriptions fit. And we have the same time evolution, apart from some fluctuations, oscillating fluctuations, that disappear as we put more solitons in the simulation. Okay. And here I have represented an animation of the probability density function for 12,000 solitons. We have the Schrödinger equation and the simulation, and we see that they fit apart from some fluctuations, which disappear as we put more solitons. Okay, then we can conclude on this part that it seems that our theory, or it seems that the Schrödinger equation, at least in this case, arises from our theory. So in some way, we have placed the Schrödinger equation in a relativistic environment, in a relativistic theory. Okay, now we want to simulate solitons at relativistic velocities. And we want to compare the results of this simulation with some theoretical results. But we see that we are not able to do it because we only have two equations describing quantum phenomena at relativistic regime. One of them is the Dirac equation, which gives us a positive defined probability density function, which is what we need to compare with the results of the simulation. But it only works for particles of spin 1/2. And it's not our case because we are restricted to one dimension. So particles can have spin. And then we have the Klein-Gordon equation, which works for particles of spin 0. So fantastic for us, but it does not give a positive defined probability density function. So we cannot compare our results with the results that we can get from this equation. Then we would like to have a relativistic version of the Schrödinger equation, but we don't have them. So maybe in this case, we will be able to see how a relativistic version of the Schrödinger equation would look like performing simulations. So, well, since we don't have any theoretical result on where we can rely, we will wonder what happens if we take this uncertainty principle, the one we get for low relativistic velocities, and well, this is not a constant uncertainty principle, so we cannot apply the recipe of reference 2. But we wonder what would happen if from this we calculate an effective Planck constant and we substitute this Planck constant in the Schrödinger equation. Will this description follow better the results of the simulations? And we see that not at all. Here we have represented the same quantity as before. The blue line is the simulation, in this case 4,000 solitons, for different velocities. And the green line is this Schrödinger equation with the effective Planck constant. And we see that it's completely far away from the simulated evolution. And actually, the original Schrödinger equation, it's closer. But we also see a strange phenomena, which is that, well, we see this phenomena as the velocity grows, and it gives an initial oscillation, kind of a thermalization. And this makes me think that we are not giving the right initial conditions to the particles. Particles don't feel stable with these initial conditions and perform a first oscillations, and then they arrived at a more stable state. Okay. Here I have done also another animation for the case of 0.8 velocity, and we see these oscillations of the probability density function. So something is not stable, is not right here, and it's happening this phenomenon. And then it gets more or less stable in a final state. Okay. Then to conclude, we have reproduced the results of reference 1, but using a relativistic theory. And therefore, we have kind of placed the Schrödinger equation in a relativistic theory. So the Schrödinger equation arises in this theory at the non-relativistic regime. And maybe this gives us a starting point to find a relativistic version of the Schrödinger equation. And well, we have to work further on finding right and realistic initial conditions at the relativistic regime before taking conclusions on the relativistic simulations. And well, thank you for your attention. And if you have any questions, I will be glad to answer.
Thank you. So maybe we can start from Gianluca, then me.
Thanks, Johan, for the presentation. I have to say that it was not so easy to read your master thesis because it's a bit out of my background. I try to do my best. The absence of a real introduction is a kind of a small problem, but
I should have put a better introduction.
Yeah.
No?
I know that you had to rush to present this and understand it. I have a few questions for you. The first one, if both from the report and you can stop it, yes. Yeah. Both for the report and from today's presentation, I understand that what you really did was to try to extend the framework presented by Damian